Hello viewers, welcome to CEC lectures. Myself Dr. Preeti Jagmani from Department of Computer Science, Arbat College, University of Delhi. So in this lecture of ours, which is under the topic of operating system concepts, we are going through the module of memory management. And in this module, what we have covered till in the previous lecture was we were talking about address bindings, and we have seen two types of address binding also. And today we are going to see the third type of the address binding, which is very popular one, and then we will proceed with the concept of context switching. So address binding, let me have a very quick recap of this. Address binding, basically a process of mapping one type of addresses onto another, and this is basically done at 3 times. So basically 3 types. One is compile time, another one is load time, and the third one is the dynamic address binding or execution time address binding. So we have seen compile time and the load time, and let us start with this execution time or dynamic address binding. So this is, as I have told you, that this is the most popular type of binding for scripts that are not compiled, because it only applies to variables in the program. So let us say we have a variable in the program which is encountered during the process of instructions in a script, and obviously that program is going to seek some memory space for that particular variable, and the memory would assign the space to that variable until the program sequence is finished, or unless a specific instructions within the script released the memory which is connected to that variable. So for example, kind of that particular memory is no longer needed, or let's say that's a pointer which is being freed. So this memory would assign the space to the variable unless there is a instruction in the program which is going to free that particular memory, or which is going to release that particular memory. Now the main program is actually loaded into the memory and it starts the execution. And when a routine needs to call another routine, or when a function, a submodule is going to call another module, the calling routine first checks to see whether other routine has been loaded or not. Now assume that the calling routine, when checked that the routine which is going to be called next has not been loaded, then the relocatable linking loader is called to load the desired routine into the memory. So calling program or calling module is going to check that the module which is going to be called next is present inside the memory, yes or no. If it is present inside the memory, already loaded, well and good. If it is not, then relocatable linking loader is called, and the desired routine is loaded into the memory. Now it's not only sufficient just to take the module and load into the memory. No, the program's address tables are also needed to be updated in order to reflect this change, because this change has to be reflected everywhere, and then only the control is passed to the newly loaded routine. So when let's say for example we have written main in C or C++, or let's say in Java. So that particular main or main, if it is calling the function f1, then, and if f1 is not available, it is being loaded into the memory, and this change is also to be kind of reflected into the program's address table, and then only the control will be passed to that function f1 for its own execution. And this is what you call the dynamic loading. That means the loading of the subroutines is actually done at the time of execution when your program is getting executed, and when, if it is the module is not available, it is called then and there. So it is known as dynamic loading. And what is the advantage of this dynamic loading is, as we have seen, that routine is loaded only when it is needed. Now let's say the program we have, whatever program we are dealing with is very, very large, and there are some routines which are very important but infrequent. Infrequent as in they need not to be kind of accessed again and again, because it's there are rare chances of occurring these routines. So for example, let's say error routines we have, so they are very useful, but when large amount of codes are needed to handle these infrequent occurring cases such as error routines, this dynamic loading is, we can say, this dynamic loading is going to work as the savior. So in this case, the total program size may be large, but the portion which is to be used and hence loaded may be much smaller, because we have already decided for dynamic loading, and so as and when the routines are required, those will be loaded into the memory. So for example, during a program execution, the error routine is not required at all. So we need not to keep that error routine into the memory and take that kind of pain, we can say. So but the dynamic loading, how it is going to be done, as we have seen that the compile time loading is done by the compiler, then load time address mapping is done by the module of the operating system, which is the loader. Dynamic loading, when we talk about, it does not require any special support from the operating system. It is done inside the application. That means it is the responsibility of the user to design the programs to take the advantage of such method. And in all the programming languages, we have such methods which are based on the technique of this dynamic loading. Operating system may help the programmer, however, by providing the library routines to implement dynamic loading. Whatever whatever library routines are required for the implementation of dynamic loading, that can be provided to the programmer by the operating system, but calling those routines and proper executing those routines is actually the we can say is the job of the programmer only. And the dynamic loading has been necessary for the entire program and all data of a process to be in physical memory for the process to execute, and the size of process is very limited to the size of physical memory. So we are aware that the size of physical memory we have is limited, and if we are looking for better memory space utilization, we need to use dynamic loading, because in dynamic loading every we can say the whole entire program and all data need not to be there present physically, so they can be called as and when required. All the routines are kept on the disk in a relocatable load format until they are called to be loaded. So as and when they are required by the program, they are called to be loaded. They are already available on the disk, and then already available on the disk in a relocatable load format, and hence they can be loaded, we can say. Now when we talk about this thing which is accessing the memory and which is kind of taking one process from disk to memory and then coming back to this. So how is actually these all processes are being done? So in this we have already seen what is address binding and what are its type. Now let's see how this memory management is being actually worked out. So we have some runtime mapping from virtual memory to physical addresses, and who is going to take care of this? This is being done by the memory management unit, which is part of your operating system, and this is actually a we can say yes, it is being not a part of operating system, it is being controlled by operating system, because this memory management unit is actually a hardware device. So yes, sorry, that cannot be a part of operating system, but yes, that can be controlled by operating system. So we have one memory management unit pronounced in short as MMU, which is we can say a scheme that is the generalization of base register scheme. And please recall that in our previous lectures we have seen this base register and the limit register also, and now here in this context this base register is now called a relocation register. Now, why are we calling this relocation register? Because the value in the relocation register is added to every address generated by the user process at the time of address is sent to the memory. So, for example, my relocation register is having a value X and the address generated by the user process is Y. So, the total address will be Y plus X. So, for example, if my base register, which is my relocation register, is at 14,000 and there is an kind of call or there is an attempt by the user to address the location 0, then the dynamically relocated address or location would be 14,000, because 14,000 plus 0 is 14,000. And for example, my program or a user process is actually trying to access the location number 345, then this location number 345 will be actually mapped and translated into 14,345, because 14,000 is already in your base register. So, here is a figure through which we can understand the concept of this base register, which is being handled by this memory management unit. So, we have CPU, a logical address, let us say 346 is being generated, and my relocation register, which is actually my base register, is giving the base value of 14,000. And now if the user process wants to access this address, so the total address translate into 14,346th location of the physical address, and it will be stored inside the physical memory on 14346 address. So, this is what the concept, and we have we can say in a different or in a tweaked form, we have also seen this particular step in our previous lectures as well. Now, apart from this task of we can say generation of the addresses which are the physical addresses. So, basically apart from this mapping and then generating the addresses, there is one more very important concept which is there, and that concept is known as swapping. Now, we have seen that data which is to be kind of accessed by CPU has to be in memory or a register, but on the other hand we are also claiming that the memory is it's not an unlimited memory, or as compared to the other memories like disk or kind of other auxiliary memories, our random access memory is in we can say in some limited amount. So, then there has to be a process of swapping. This process also referred to as memory concept. So, this process of swapping says, as and when because of the memory limitation, keep your data onto the disk, and as and when required, take that data from the disk, load it into the memory, and if the memory is full, some data from the memory will also go to the disk for some times. So, basically this is what you call process of swapping. This process of swapping, although at first instance it seems that it is going to affect the performance of the system, because there is kind of to and fro movement of the data from the memory to disk. Okay, agree. But when we have more than one processes and we have larger programs, then the process of swapping is going to actually, we can say affect the performance of the program. Yes, in some cases, but it helps to learn the larger and more than one processes. The process is large and more than one processes are there, then it is going to help. Now, how it is going to help, we will see, and where what all are the scenarios in which this swapping could be we can say detrimental action, that we will see in a while. So, the concept of swapping basically, as you have seen, is divided into two sub concepts, which is swap in and swap out. So, swap out, as the name indicates, method of removing a process from RAM and adding it to the hard disk. So, from RAM the process has been swapped out, added to the hard disk. Contrary to this, the opposite is swap in, which is a method of removing a program from a hard disk and putting it into the main memory or the random access memory, that is swap in. So, if process is coming inside the memory, swap in. If process is going outside the memory from memory to disk, that is swap out. Now, we need to see why this swapping is to be performed. Definitely, being a very important process, there are some advantages, also some disadvantages of swapping. So, the advantages, if we see, that it helps the CPU to manage multiple processes within a single main memory. So, basically we can say it is going to increase the degree of multi-programming, we can say, and in this context it also helps to create and use virtual memory. Now, virtual memory is basically what? Virtual memory is your disk. So, basically that is called virtual memory, and we will be taking this concept of virtual memory in quite a greater detail in our upcoming lectures. Now, swapping also allows the CPU to perform multiple tasks simultaneously. For example, a process is busy with some input output and there is no process in the memory, then the one process from the disk will be loaded into the memory and given to CPU, and then it will start kind of execution. So, the processes do not have to wait very long before they are executed. So, basically it is going to, we can say, improve the performance, it is going to improve the utilization of main memory. But with this, there are some consequences, there are some disadvantages of swapping. That is, if the computer system loses power while the processes are being swapped, then a user may lose all the information which is related to the program if it is kind of a swapping activity which is going on. And if the swapping algorithm, there are different algorithms for swapping, that which process is to be swapped when, those this answer is to be taken out by applying a swapping algorithm. So, if that swapping algorithm is not good or not optimum, this composite method can increase the number of page faults and decrease the overall processing performance. So, in order to explain this or in order to understand this, let us take a scenario that there are three processes which are onto the disk and we have very physical, very little physical memory. The process 1 is being kind of swapped here, then immediately there is turn of process 2, then your process 1 is being transferred to the disk again, process 2 is brought here in the main memory, and this kind of high degree of swapping is going on. So, if high degree of swapping is going on, that means your swapping algorithm is somewhere faulty, and if the system is always busy doing some time doing some kind of swapping, then it will decrease the overall processing performance, because more than the execution, it is the swapping which is going on, and that was not the agenda. The swapping was there only to kind of, we can say, supplement or only to augment into the performance. Now, whenever a process is being either swapped in or swapped out, there is one more fundamental concept of context switching which comes into the light, and we have already seen this context switching in the during the process of memory management, and I am just kind of recapping that context switching process here, because this is also a place where that context switching should be kind of considered, we can say. So, basically a context switching is a technique or method which is used by operating system in order to switch a process from one state to another in order to execute its functions using the CPU in the system. So, for example, whenever a CPU is going to change a process, let us say for example from process number 1, the CPU wants to go to process number 2, then it is going to store the status of the process number 1 till which that process number 1 has been completed or executed. Then this whole state is saved in the form of registers, and then only a CPU is being assigned a new process in order to carry on with. Now, when the new process which is running in the system is done with its part, this the new process will go out of the system, and the previous one, which was the process 1, has to be restored in order to take up. And this previous process, the question lies that this previous where this previous process is being kind of kept. So this previous process must wait in a ready queue. Then the execution of the old process will obviously start at the point where the another process stopped it, and that's way that maintaining the status is important, so that from that particular point it can be resumed. And now we can also say that the characteristics of a multitasking operating system in which multiple processes are going to share the same CPU to perform their own task without the need for additional processor in the system. That means there is one CPU and there are more than one processes, more than one task which are looking for CPU. So yes, you need some kind of context switching there. Now this context switching, how this is going to be kind of we can say executed. So this context switching can be executed with the help of, the simplest idea is the standard swapping. The standard swapping involves the movement of processes between the main memory and the disk, we can say, or any backing storage which is the disk. The system maintains a ready queue, as I have already told you, consisting of all the processes whose memory images are on the disk or in memory and they are ready to run. So basically there is a ready queue whose images are available either in the memory or on the disk, and these processes are ready to run. So whenever the CPU scheduler decides to execute the process, it calls the dispatcher, and the dispatcher checks to see whether the next process in the queue is in the memory. So if the next process which is to be dispatch as in which is going to take the control of CPU is already available in the memory. If it is available in the memory, well and good. If it is not available in the memory, also there is no free memory region in order to load that process. The dispatcher swaps out a process which is already there in the memory and then swaps in the desired process. So basically we will say, let's say for example the ready queue says now we need to execute, let's say, process X, and this process X is first of all not available in the memory. The second thing, that the memory is not free. Then any other process, let's say a process Y or maybe a process X dash, will be taken out from the memory, will be stored in the disk, and now at the place of this process X dash or process Y, this process X will be placed. And yes, a proper kind of relocation of registers, proper transferring of control to the selected process has to be done. So if you can see here is a diagram on the screen which explains this process of swapping. So operating system and is residing inside the main memory, and we have a separate user space which is available for various processes. Now there are some processes, for example process P1 and process P2, which are waiting, which are stored at the backing store. Backing store here is actually your hard disk. So process P1 is currently being swapped out. Earlier, that means earlier it was available inside the memory and now it was swapped out in order to, we can say, in order to accommodate the process P2, which is going to be swapped in from the backing store to the main memory. So, this movement of processes is actually a swapping. Now, if you can see, the major part of this activity is about the transfer time, and as far as transfer time is concerned, we can say, larger the process or bulky the process, more is going to be the transfer time here. That is one thing which is very, very sure, that major part of swapping is taken by the transfer time, and this total transfer time is directly proportional to the amount of memory swapped. Also, one important thing, if we want to swap a particular process, we also need to ensure that it is idle. That means it is not having any pending input output which is going on, or it is not having any input output operation in waiting when we want to swap that particular memory, we can say. So, here in this lecture, what we have seen till this point is what is the context switching, and whenever we talk about this context switching, there is a process of swapping which comes in terms of memory management, and the standard process of swapping involves two movements. One is a swap in and another one is a swap out. But one thing which is to be some points which are to be taken care for this swapping in and swapping out is, one is the dispatcher is the module which is involved in this swapping in and swapping out. Also, we need to see what are the algorithms which are going to take place in order to decide which process will be swapped out in order to accommodate another process that we will be seeing hopefully in the next lecture. Then how this particular process is being done of swapping in and swapping out by kind of maintaining the storing the current state and then resuming the process from that particular state only, and so on and so forth, and which processes we can swap out, that also need to be kind of very carefully chosen. That means those processes should be we can say idle. They should not have any pending input output, or they should not be waiting for any input output when they are being swapped in order to free the memory, because then in that situation this is going to be an operation which results in an inconsistency, or it could be a very, very costly operation. So, we have seen swapping and its related fundamentals in this lecture, and here is a list of references which is being used for the preparation of lecture. Hope you have enjoyed one. Thank you for patient hearing. I will see you in the next lecture. Till then, please take care. Goodbye.